No, good point. That was a good call. Okay? This point right here is the point 5, 1/5. Okay? As we move this rectangle up, the rectangle is a constant length of 1 until we get to this point 5. Then the rectangle starts changing its length because the left end point is on this line, x equals 4. The right end point is on the curve itself. So we have two separate integrals to set up for this volume. Just the way it is. First volume is, let's do it. We're going to get, when we take this rectangle around the x-axis, we're going to get a shell. So the first volume is 2 pi, the integral. Y goes from 0 to 1/5. Okay. RH. Okay. Now what is R? As this gets whipped around the x-axis, this distance right here is R. What is that's equal to y. It's the height above the x-axis, which is y. H is this length right here. What is that length right there? 1, correct. dy. So the first volume that we get is going to be this here. Okay? All right, we all set on that? So let's do it. 2 pi, integral y dy, y squared over 2, 0 to 1/5. We'll end up with y squared, 1/25, so it's pi over 25. Okay. All right. Another way to look at that is this. If you were to take this area right here, this rectangle, and whip it around the x-axis, we would generate a cylinder. And what's the volume of that cylinder? The volume of a cylinder is pi r squared h. What's r? R would be this radius from here to here. Okay? That radius would be half of this 1/5, would be 1/10. It would be pi r squared h, where h would be equal to 1. And you could set it up that way. The r would be the 1/5, okay? This distance right here. So as you whipped it around this way, what's the volume of that cylinder? Okay, this is a radius of 1/5. This is 1. What's the volume of the cylinder? It's pi r squared h. Okay, it would be pi 1/5 squared h. So you get pi over 25. That's what we got here.
Why isn't it just 25 pi? Why is it over 25?
Because the radius is 1/5. Going from here to here is only up to 1/5.
Oh, okay.
Okay? So I'm saying you could have done it that way without the calculus. Now, that's part of it. The second part, we're going to go from here up to here. Okay? So, second part, second volume is equal to, and again, that rectangle is going to generate a shell. It's going to be 2 pi. Now, what's R here? Let me draw another diagram here. Okay. We're going from here. Let's see, that's 4. Let's see, this is 5. So this is the part that we want now, right up here. As this part goes whipping around the x-axis, okay? Okay, right here. All right, so what do we got? What's R now? What's R equal to? This height right here, what's that equal to? What is it? From here to here?
Y.
It's y. It's y. Just plain y. The height above the x-axis is y. Okay? Y. Okay. The y's are going to go from, where are the y's going to go, by the way? They're going to go from here, 1/5, to here, 1/4. The y limits are going to go from 1/5 up to 1/4. Okay? 2 pi r, this, here, h. What is this length equal to? This is the tricky part right here. What is this length right here? This is the length of this rectangle. It's equal to what? It's equal What is it?
X minus delta x.
All right, well, let's see. It's this distance from the y-axis, which is x. I agree. But what's x equal to? You got to get it in terms of y. So solve for x, which is equal to 1 over y. It's equal to this x minus this distance, which is equal to 4. Yeah. That will be the volume generated by taking this, right here, this piece about the x-axis. I don't know what to tell you, except that's what it would be. By far, the better way would be to take the rectangles this way and have only one volume, okay, and use discs. It would be much easier.
I just want you to do this way.
What's that?
Just wants you to struggle.
They want you to struggle, yeah. No, they want you to use shells.
I mean, on a test, could we use whatever way that we?
Actually, no. Here's what happens on a test. On this section, I give you some areas, and I say, set up the integral that gives the volume of the solid revolution generated by taking that area about, say, the x-axis. And then I'll have the integrals. And they'll all be in terms of x, say. And so you have to pick the integral out that gives you the volume. And then I'll say, find the integral that gives the volume when the area is about the line x equals 1 or y equals negative 1. There'll be a washer, a disc, a shell, that kind of a thing. I wouldn't give you one like this.
For the test, we just need to know the 3 methods.
There's only 3 methods ever.
Yeah, so I'm just saying, that's all that's going to be in the test, really.
So on the test, you'll have one of those 3, yes. And you can always tell if the rectangle chosen is perpendicular to the axis, you will either have a disc, if there's no gap, or you'll have a washer if there is. And if it's parallel to the axis, it'll always be a shell. And that's why when you take this rectangle around the x-axis, it's going to be a shell, because these are parallel. Okay? Now, how do you do this integral? Well, you multiply through. The integral itself is not bad. Okay? It's just a pain in the neck to set up. Okay? All right, there's that one. Number 8. Oh, that was question number 6.
Wait, can you put that back up?
Yeah.
I was just watching that.
Now, Danielle, have you been able to access the notes on WebAssign?
I will.
I think these
Sorry.
might be a little easier.
Oh,
Like
yeah.
really playing, I got to the other class.
Chuck, you all set with this?
Yes, thank you.
All right, next one. It says use the shell method to find the volume of the solid generated revolving the plane region about the line x equal 5. And it's got y equals the square root of x at y equals 0, x equals 1.
What was the question? About what axis?
About the line x equal 5. So y equals the square root of x. Y equals 0, that's the x-axis. X equals 1. About the line x equals 5. So we're taking this area about this line as it gets whipped around that line. And what they want you to use are shells. So to use shells, what we're going to do is take a rectangle this way. As we whip this around that line x equal 5, we'll get a shell. The volume will be 2 pi, the integral. Now, x is going to go from 0 to 1. R. This distance will be r from here to here as this gets whipped around this line. What is that distance r?
Square root of x.
No, the square root of x would be this height right here.
Oh, so it's just
Delta x minus or plus 5. That would-
All right, hold on now. Whenever you're looking for r's and h's in these things, you'll never use a delta x or a delta y. The delta x and delta y is the thing at the end here.
So just that.
Okay, well, x is this distance.
5. There you go.
Correct. That's what we need. This distance is 5. This distance is x. The distance from the y-axis is x. The radius that we're looking for is going to be 5 minus x. Okay? It's the kind of thing you're going to have to be able to do. Okay? It's fairly typical when you do these problems. Okay? 5 is this distance, x is this, so this, what we're looking for, is 5 minus x. H is this height, and that is equal to the square root of x. That is correct. It's equal to y, which is the square root of x. Okay. Now, again, the integral is not bad. It's just setting up the integral. To do the integral, multiply it out. Integrate it, 5x to the 1/2. Add 1, divide by the new exponent. Substitute in. Okay. You're going to get 10/3 minus 2/5. Zeros give you 0. We get 4488 okay, is the answer that you'd get
Is
there.
that 88 pi over 50?
Yep. Yep. And that's what you would get. And I'm pretty sure that's the kind of thing that WebAssign wants, that answer, just like that.
Yeah.
Yep. Okay, everybody all set on that? On the test, I'm going to be asking for this. Okay, right here. Set up the integral. Okay, that's what I'm going to ask for.
I'm gonna take a look for a second.
Okay.
Just that one step?
Yeah.
You're the best.
Think I ought to do more then?
No, not at all.
Okay, that's a good idea.
On the previous round, was it 1/4 minus y? On the previous one.
The previous one, what about it?
On the last equation, is it, oh, it's 1 y.
It's 1 over y minus 4. Let's see, this. Okay. R. This distance here, this distance is equal to. Okay, where am I going around? I'm going around this way. Okay. It's equal to this. Jeez, what the heck did I have here? All right, it was equal to 2 pi r, and we were going around the x-axis. Okay. So when we were going around the x-axis, it was 2 pi r, and r is the height above the x-axis is y, and then h is this distance. Well, what is this distance? It's equal to this distance, x, which is 1 over y, minus this distance, 4. Yeah, that's it. Yeah, that was it. All right, anybody else in on that? Just looked a little weird, you know? Last one. Set up the definite integral that gives the area of the region. Okay. Wow. What's that? Here we go. y1 is x squared plus 2x plus 1. y2 is 2x plus 5. Bless you.
Thank you.
X squared plus 2x plus 1 is a parabola something like this. Y equals 2x plus 5, something like this. And we want this area right here. Well, to find that area, bounded by the 2, we're going to have to take the integral of the top minus the bottom. But the problem here is not this. This part's pretty simple. The problem is, what are these points? Well, what's that? Well, set them equal to each other. Yeah, and let's do it. So you set these equal to each other. X squared plus 2x plus 1 equals the 2x plus 5. Subtract the 2x's, okay? Actually, from here, you could subtract a 1 and get x is plus or minus 2. So when x is negative 2, the y is 1. When x is positive 2, this is 9. Okay? So you get these 2 points. And the integral then goes from negative 2 to 2. Okay? So that wouldn't be too bad. Any questions on that? That's it, Melissa?
That's it.
Cool. Any other questions? Okay. Let's move on. What? Wait, so where'd this cable come from?
I was sitting there.
We're sitting here?
I'll take it.
Oh, wait, this is the one I brought in. Because this one was here or something, right? We're just,
It's been there for weeks.
and it's still loose, but it works.
Well, yeah, it's broken.
Okay. So, you know what happened on Friday?
Oh, how'd it go?
Well, it went well, except it was on the left side, not the right side, first of all.
Did they help you though?
Yeah, there was a guy there that helped out, and he put the cable in there, and it worked out pretty well. But I was on this little podium thing with my laptop. I was really uncomfortable.
Not intuitive.
It wasn't good. I wasn't my usual humorous self, you know what I mean? I was really uncomfortable, and it wasn't all that good. What's that?
What happened Friday?
I gave this presentation to the technology division on using Mathematica, and I wrote this, what I thought was a cool little program on light sources.
Were they impressed?
No, they weren't. But that was because of me, though, because I lost some of my pizzazz because I was uncomfortable. I had a microphone, too.
You got a microphone?
I had to hold a microphone, which kept on fading in and out, and try to work the thing, and I'm not good doing something like that.
I'll
You know?
help you next time.
Yeah, that's, all right. All right. There won't be a next time.
Maybe you need like a headset, like a microphone that's
Yeah, something, it just didn't work really well. So, I don't know. Okay, let's move on. All right, here's what we're doing the rest of this chapter. We're doing additional applications of the integral. We're using the integral to solve certain problems. One typical kind of a problem would be something like this. Let's suppose we have some function.
So we're not doing shelves and washers anymore.
No, we're done. I finished that. Now, if you have a question on them on Thursday, bring them in.
No, I don't know if what we're learning is based off of that.
No,
Okay.
no, it's going to be totally different. We've got some function, and here's the question. We want to find the length of this curve from here to here. We want to find the distance traveled along this path. If somebody were walking along this path, what is the length of that path? Okay, what's the length of that curve? If you're putting up telephone wire, all right, and you got this path of telephone wire, you want to know what the length of the path is. How much wire do you need? Okay, that's the catenary curve. Okay, you'd want to know the length of that catenary curve. There's a lot of applications for the length of a curve like this. Well, how are we going to do this? We're going to do this by doing some approximations first. Let's take this and let's divide this up into delta x. Okay, a whole bunch of delta x's. Let me just take this delta x. Now let me take this part of it out. So we have this. This is my delta x, right here. If you draw this little right triangle right here, okay, take this over to here. This is delta x. This would be delta y. And what we're going to do is use this hypotenuse of that right triangle as an approximation excuse me, as approximation of that arc length over that interval. Okay? That's what we're going to use. So that arc length, I'll call it L sub I, is approximately equal to the square root of delta x squared plus delta y squared. Okay? That's the hypotenuse for the right triangle, and I'm going to use that as an approximation for the arc length over that interval. Okay? Well, I can sum up all those approximations to get an approximation for the arc length of this curve. If I divided this up into n little subintervals, I take the sum of all these little subintervals, like so.
So the little triangles.
The little triangles are the little delta x's. Okay, this is the delta x here. This delta x and a delta y. Change in x over the change in the change in y.
Wait, but what's the summation?
The summation is I'm adding up all these delta x's. So here's another one.
Yeah, that's what I was asking.
Yeah. There's a delta x here. There's a delta x here. There's all the way across.
And you tried to find the area?
No, I'm trying to find the sum of all these hypotenuses to get the length of the curve. That's what I'm trying to do. Get the length of the curve.
You can't use the integral for that?
I'm headed there. I'm headed there. The integral, if we integrate the function, we know we get an area. It doesn't give us arc length. But what we're headed for is a way of using the integral to get the arc length. Now here's the problem. The problem is this is not the right form. To get the right form, I need a Riemann sum. To get the right form, what I'm after is something that looks like this. What I need is a Riemann sum that looks like this. The limit as n goes to infinity of the sum, some function of x times a delta x. This is the kind of thing I want. Okay? This is what we did for our volumes of solids of revolution. If we could get it into this form, where this maybe is a pi r squared, or maybe it was a 2 pi r h, or maybe it was a pi big R squared minus little r squared, if we could get it to look like this, we can evaluate it with an integral. If we could get it to look like this. We don't have that here, but we can get there. We're going to do the following. Okay? I'm going to take, first of all, I am going to take the limit as n goes to infinity. All right, so the exact length is going to be the limit as n goes to infinity of the sum okay, but it doesn't look like this. What I'm going to have to do is make some changes. Oh boy, I'm running out of space. All right, you guys okay? I'm going to move this up a little bit. So my length is equal to the limit n goes to infinity. What I'm going to do is multiply and divide by a delta x. I'm going to multiply and divide by a delta x. Now all I've done is multiply by 1, so that's legal. I can do such a thing. This delta x down here, I'm going to treat it as a square root of delta x squared. Square root of delta x squared is still delta x. Why do that? That enables me to combine these into one square root. Okay, 1 to n, jeez, arg. Okay, square root of, I have a delta x squared over delta x squared, that's a 1 plus, that's this one, delta y over delta x squared times a delta x. All right, check that out. Make sure that makes some sense. What do you think, Trent? It's reasonable, right? Now, here's the big question. As n goes to infinity, what happens with delta x as n goes to infinity? Goes to 0. That's correct. What happens to delta y as n goes to infinity? Also goes to 0. Very good.
How do you know that? Is it just from the picture?
Yeah, because the delta x is that interval from A to B. If I divide it up into n parts, each delta x is going to be b minus a over n. And if I let n go to infinity, the b minus a over n is going to go to 0. The delta x is going to get smaller and smaller and smaller and go to 0. Now, here's the thing. I need someone to tell me what the limit of delta y over delta x is as the delta x goes to 0. What is this ratio equal to as delta x goes to 0? As n goes to infinity and delta x goes to 0, what happens to delta y over delta x? Where does it go? What? Possibly.
Because if y is getting smaller.
Yeah, y is getting smaller, the delta x is getting smaller. But there is an actual limit. There is something it could be infinity, but it could be 1. It's possible it's 1.
Just shoot out answers.
It could be the slope of the tangent line. Another word for that is the derivative. Thank you. That's exactly what a derivative. That's the derivative right there. As n goes to infinity and delta x goes to 0, what's the limit of delta y over delta x as delta x goes to 0? That's the definition of a derivative. That's a derivative. Okay? So what do we have? Here's what we have. We have this. Arc length is equal to the limit as n goes to infinity of the sum square root up 1 plus the derivative squared delta x. And guess what we have here? We have a Riemann sum. If y is a function of x, the derivative of y with respect to x is a function of x squared. Add 1, take the square root. This is some function of x times the delta x. That's a Riemann sum. What's arc length equal to? The integral from a to b, square root of 1 plus the derivative squared. Directly from this. Okay? That's the arc length of a curve.
Good stuff.
It's good stuff, is right. It's really good. Let's do one. Unfortunately, here's the bad news. The bad news is there's not many functions we can actually take a derivative, square it, add 1, take the square root, and then integrate the thing. Okay? Well, we can take a simple example just to verify this. Okay? So here we go. You ready?
Let's use a Webber-Side example.
What's that? Well, the Webber sign you get y to the 3 halves. That's the typical one. Its derivative is 3 halves x to the 1 half. Then you can square it, and then you can take the integral. But I'm going to do a simple one here. Let's just do one where we can verify. Let's do y equals 5x. And let's have x go from 0 to 1. And let's verify this. And again, what I would do on the test is ask you to set up the integral that gives the arc length, okay, rather than actually do the integral. Y equals 5x is this.
We're supposed to pretty much find the hypotenuse.
Yeah, that's exactly right. That's all we're going to do here. So the length of this curve is the hypotenuse of this right triangle, which is what Nick just said. Or use a distance formula. The length of this curve is going to be the square root of 1 squared plus 5 squared, square root of 26. Let's use the integral and let's verify that. Okay? That's all I want to do here is verify this. This formula, by the way, when you get to Calc 3 and do parametric forms, comes into play again. You'll revisit this formula, but now you'll do it in terms of a parametrically defined function. So you can do more interesting things, like find circumference of a circle and things like that that are defined parametrically.
How do you find the derivative of...
Let's do it. Find the derivative. All right, we got the integral from a to b, 0 to 1. Square root of 1 plus the derivative. What's the derivative of 5x?
5.
5 squared. Okay, derivative squared. Okay. That's a square root of 26. That's a constant. You can bring that out front. What's the integral of dx? X. Okay. Okay, Jeff. Got away. Okay? How we doing? That's it.
Can we do one with something like the first one? The actual thing you're using?
What's that?
I was like,
The actual, can we use that curve?
I can do this all.
No. The problem with those things are, if you take their derivatives, then you square them and add 1, and then take the square root, you can't integrate them.
Wait, so we use that to find this equation, but we can't use it to...
Well, I could give you one. Actually, there's a whole class of functions that are specifically designed so that they will come out. After you take a derivative, you square it, you add 1, it comes out to be a perfect square. Then you can take the square root, and then you can integrate it. But those are artificially created and not really important. Well, we can do one. Here, let's do the usual then. I think this is part of your homework, but we can take a look at it. Let's take x to the 3/2. Let's go from 0 to, say, 4. Here's what we got. Okay. 0. At 4, we have 8. So it looks like something like this. It goes up like this. Okay. And we want to find the length of this curve over this interval. Okay. So here we go. The length is equal to the integral, 0 to 4. Square root of. This is right here is what you have to know. This here, right here. Square root of 1 plus the derivative. Now the derivative is 3/2 x to the 1/2 squared dx. Okay. Okay. So that's equal to the integral from 0 to 4, square root of 1 plus 9/4 x dx. Well, that's not too bad. How do we integrate this thing? What form is it? U to the n form. It's exactly what it is. Let u equal 1 plus 9/4 x. The du is 9/4 dx. Okay. Multiply by 9/4 and by 4/9 to get this integral. 4/9. The integral is x goes from 0 to 4. Okay. U to the 1/2 du. A u to the n form. Okay. What are you guys doing in a day? We
just finished 7.3.
7.3. What's that, shells?
Yes.
Okay, well, I'm
Reason of the day.
so I'm a little bit
You're on
heavy.
time. Yeah.
Yeah. Is she going to give her test before the spring break?
Oh.
Ooh, that's going to be a little tight, huh? But you could be
She
done.
is. I don't know. I have no idea.
She said she's not.
She's
Yeah.
not? Ooh.
She asked if we were gonna have one, I said, yeah.
And then she,
And she laughed and walked away.
she laughed. Is that right? Yikes, I don't know. What does that mean? Anyhow, yeah, we'll have the test beforehand, yeah. Okay, so
Is it unusual laugh?
So-
There was nothing.
4/9, the integral of u to the 1/2 is u to the 3 halves, where u is 1 plus 9/4 x to the 3 halves times 2/3 from 0 to 4. They get a little messy. Even this one gets messy. I don't know. Yeah.
Can we just leave it at that then?
What's that?
Can we just leave it at that?
On the test, I'll just have you set it up. I'd leave it back here somewhere. All right, then you get 8/27. Let's see. When you substitute in 4, you get a 4 here. Now watch what happens here. This is you may get this on. You probably will get this on WebAssign. What happens here when you substitute a 4 in, the 4's cancel. You get 1 plus 9, 10 to the 3 halves, and that's 10 square roots of 10. Okay, 10 to the 3 halves, 10 square roots of 10.
Wait, where did you get that? I'm sorry.
Okay, stick a 4 in for x.
And you get cancel out 4.
Okay, it's off the 4's. You get 1 plus 9.
Oh, 10.
10 to the 3 halves. That's 10 square roots of 10. That's what 10 to the 3 halves is. 10 square roots of 10. Minus the 0. When you substitute in 0, you get 0 here, but you still got this 1 here. That's your answer. That's typical of these arc length problems like this. Okay. Yes.
Wouldn't you have it cubed inside the 10 or no?
When you take 10 to the 3 halves, you take the square root of 10 cubed. But what's the square root of 10 cubed? It's the square root of 10, square root of 10, square root of 10. Square root of 10 times the square root of 10 is 10 times the square root of 10. So you get 10 square roots of 10. That's what you get. That's typical of these problems. Well, that's arc length. Okay? Like I said, at Calc 3, you come back to that when you do the functions defined parametrically. It's kind of nice there. All right, you ready to go on? Okay. What's next?
We're only doing one section today, right?
So, we got much to do. Lots to go. What time is it? We got a long way to go. Long way to go. Okay, here's what we're going to do next. This is surface area. This is the same thing as the arc length. So this would also be 7.4, I think. 7.4 would be arc length and surface area. Okay, surface area. Here's what we're going to do now. We're going to take a function. Okay, and we're going to take this and whip it around the x-axis. Or whip it around the y-axis. But let's go with the x-axis first. When we do such a thing, we're going to generate a solid of revolution. We know that. We know how to find its volume. Matter of fact, in this case, what we would do is have disks, and we would use pi r squared dx, and it would be not a big deal. But here's what we want now. We want to find the surface area of that solid of revolution. Okay? We want to find the surface area. Okay? As this thing gets whipped around, okay, the x-axis, we're going to generate the solid of revolution, okay, and we want its surface area. Now, not included the two bases. We want just the surface area. So if you're working for GE and you're designing this an engine casing that looks just like this, okay, and you have to find out how much certain kind of coating you're going to have to put on this thing, okay, it would be the surface area that you would have to figure out as how much coating you're going to have to put on it. Or if this is a certain steel or whatever you're going to use here, carbon fiber or whatever the heck you're going to use, how much is it you're going to use? It would be a surface area. Okay, that would be the surface area of the thing. So that's what you want to do, is find out the surface area of this thing. Well, what do you think we're going to do? We're going to divide this up into little pieces. We're going to take one such piece and whip it around the x-axis. We're going to see how much surface area is generated by that one piece. We're going to sum up all those pieces. We're going to let the number of pieces go to infinity. And hopefully we're going to be able to take that sum and make it into a Riemann sum. So we can evaluate it with an integral. That's our goal. Okay? So let's do it. What's that?
Arc length to infinity?
Well, arc length is going to play a role. Let's take a look. Arc length will play a role here. We're going to take this piece of arc length here and whip it around, okay, the x-axis. Okay? Here, call this L sub I, a little piece of arc length, as it gets whipped around the x-axis. Okay? I don't know how good that is. But you can imagine, we'll take a piece of arc length and whip it around the x-axis. That arc length is going to generate some area. Now, here's what we're going to do. I'm going to take this, say this point, and call this R sub I. Okay? Now, so, here's my little piece of arc length up here. Okay? It gets whipped around the x-axis. It's going to generate some area. We want to know how much area is generated by this arc length. So what I'm going to do, I'm going to cut this. Okay? And I'm going to open it up. And what I'm going to get is something that looks rectangular. Okay? What's the area of that rectangle? The area of a rectangle is its length times its width. Its width is going to be the arc length. That's what I'm going to use for the width. What's the length of that rectangle?
Twice the radius. 2 pi?
2 pi r. It's going to be the circumference. It's going to be the circumference throughout this as this gets revolved around. Okay? It's 2 pi r L. Here, our little piece of area. Okay? This one piece is approximately equal to 2 pi r L. That's what it is. It's the circumference times an arc length. Okay? The circumference gives me the length of the rectangle, and the arc length gives me the width. What am I going to do? I'm going to sum up all these pieces. The arc length in terms of n of these will be the sum of n of these. What's my exact surface area? The exact surface area is going to be the limit, as n goes to infinity, of the sum of all these little pieces. Now, what do we got? 2 pi r L. Now, what's the L part? The L part is what we just did before. It's going to be equal to the delta x sub I over delta x sub I squared plus the delta y over delta x sub I squared times a delta x. Okay? That's what I just did before. Back here a ways. Okay? Now, I wrote it as 1. Okay. But, okay. Hopefully you can see this. This is the L part. Okay? Okay. What the L part is that square root of, it's the hypotenuse. Okay? And then multiply and divide by a delta x and in the form of the square root of delta x squared. As n goes to infinity, the delta x's will go to 0. This is equal to 1. This is equal to the derivative. This is a delta x. So we have this. The surface area is the limit as n goes to infinity of the sum of 2 pi r sub I square root of 1 plus the derivative squared delta x. Okay? This is a Riemann sum. What do we have here? This whole expression here is some function of x times a delta x. This is a Riemann sum. How do we evaluate that Riemann sum? With an integral. Surface area is equal to geez, I don't know, Nick, what order I got. I'm throwing these things over here. They're,
Whatever.
oh, man. Oh, just, all right.
See the video, you don't worry about that.
Yeah, all right. Well, anyhow, so we got that Riemann sum. So what's the surface area equal to? It's the integral. 2 pi. You can take the 2 pi out front. A to B. R, L, which is the square root of 1 plus the derivative squared dx. That's it.
Just put them in order as you go. Right?
Yeah, all right.
Not right now, I'm saying like as you're.
As I go on, yeah,
As
I'm
they
putting
go
them
on.
on top, so they're in order, I think.
Okay.
I think they're in order. Okay?
So just remember this formula.
Yeah, you're going to have to remember this formula. Now, there's two separate things here. One, if I take this arc length and I whip it around the x-axis, I'm going to generate the solid of revolution about the x-axis. About the x-axis. What's R going to be if I whip this thing around the x-axis?
The x, to the x, distance to the x. Y.
Y is what it's going to be. It's the height above the x-axis, which is y. Nice. And if I whip this thing around the y-axis, what's my R going to be in that case? X. That's the only difference in the two. Okay.
So,
Go ahead.
most of these problems, the disk, the shell, surface area, has to do with 2 pi r times h.
Basically, yeah.
And it's whatever h and r is for that
Yeah.
application.
Absolutely. Absolutely. Yep. Let's do a problem. Here we can do a problem. We can derive a formula here. Let's derive a formula for the lateral surface area of a right circular cone. Okay? So let's do it. Here we go. Let's take this line. Let's whip this line around the x-axis. When I do this, it's going to generate a right circular cone. Okay? That right circular cone will have a radius of capital R and a height of capital H. What we want to do is derive the formula for the lateral surface area of this right circular cone. Okay? The lateral surface area, what that means is it's the surface area except for the circular base. Okay? If you wanted to put the circular base in there, you'd add a pi r squared because that would be the area of the circular base. But we're talking about the lateral surface area, okay? The side of that. Let's do it. Okay, here we go. Take a rectangle. Okay? That surface area around the x-axis is going to be 2 pi. The integral. X is going to go from 0 to h. Okay. R, now this is R. What is this R equal to? It's equal to y. Okay, but what's y equal to now? When I write my rectangle this way, and I use a delta x down here, that tells me everything in the integral has to be in terms of x. I need to find out what y is in terms of x. I need the equation of this line. All right, the equation of this line is no big deal. It's y is equal to negative r over hx, okay, plus r. That's the equation of that line. Okay, m the slope, change in y over change in x, and the intercept is r. So y is equal to this. So 2 pi negative r over hx plus r. Okay, square root of 1 plus the derivative squared. What's the derivative of this? Here's my function. What's the derivative of this? My function's right here.
Negative r over h.
Thank you. And I'm going to square it. So it's going to be r squared over h squared. Okay? dx. This integral will give me the lateral surface area of that right circular cone. You ready? It's good stuff. So here we go. First of all, please note over here in the square root, I got just constants. I'm going to multiply by h squared over h squared here. And I'm going to take that out front. So I'm going to have 2 pi square root of h squared plus r squared, okay, all over h. Okay, square root of h squared is h. And then I'm going to integrate this with respect to x. And when I integrate that with respect to x, I'm going to have a negative r over h, x squared over 2, plus rx. Okay. Do. How we doing? I take it that means good. All right. So we get 2 pi square root of h squared plus r squared all over h. Let's see. Let's chuck in an h for x. So we're going to get negative r h squared over 2h plus rh minus 0 minus 0. Well, one set of h's cancel. I get here's what I have, 2 pi square root of h squared plus r squared over h. One set of h's cancel. I get a negative rh over 2 plus rh. Okay. Now, combine these into 1. I can multiply by 2 over 2. I get 2 RHs minus 1 RH. This gives me an RH over 2. So I have now 2 pi square root of h squared plus r squared over h times RH over 2. That's what this gives me right here. Multiply by 2 over 2. And now what do I get? 2's cancel, h's cancel. I end up with pi r square root of h squared plus r squared. That is the lateral surface area of a right circular cone. Not only that, this quantity right here is called the slant height of a cone. It's this distance here. Okay? And oftentimes when you look this up, you'll get pi rs for slant height, okay, would be the lateral surface area of that right circular cone.
The hypotenuse.
Yes, and that's the hypotenuse. Now, that's whipping around the x-axis. We could whip it around the y-axis. What changes? If we whip this around the y-axis, what will be different? What will be different is
H and R.
well, h and r, we're going to keep those the same. But what will change is the r for this this distance r. Whereas we just did this distance r here, and it's equal to y. When I whip it around the y-axis, this distance r is going to be equal to what?
H minus x.
What is it?
H minus x.
No. What is this distance equal to? X. That's it. It'll be an x. It'll just be an x. And believe it or not, if you do this around the y-axis, okay, you'll get the same exact thing you just got here, except instead of a big R here, you get the H here, okay? It's the only difference, okay? Because what happens is now the H, it becomes the radius of the base as you go whipping around the y-axis. That's the difference, okay? The lateral surface area is pi times the radius of the base times the slant height. But when you whip it around the y-axis, the radius of the base is going to be the h in our diagram here. So it's all basically the same. What do you think?
This is like making. We should have pizza.
Oh yeah, you're right. I see him.
Mike just got there.
What can I tell you? This is what it is. It's not that bad. What I'm going to give you on the test, I'll give you a couple where you set up the integrals to do it. It shouldn't be that bad, all right? It shouldn't be that bad.
We just gotta practice, right?
Yeah, hey, that's it. Okay, let's go on. Holy crap. No, I should give you one to do because this is way too easy. I should give you one to do. Here, you guys do one.
So fried.
Tell you what, why don't you guys do this one? This is going way too fast. Okay, here we go.
I thought we had a lot to do.
Well, only one more section now. We just did surface area, we did arc length, and all we got now are Hooke's law with a spring, and that's nothing. So I'm going to give you guys one to do. What?
I'm getting Chinese necklace.
Oh. Jeez. All right, here you go. You ready? Here's what I want you to do. Let's take a horizontal line. Let's take the line y equals capital R. Let's go from this point 0, 0 to this point H0. Okay? You're going to take this area and you're going to whip it around the x-axis.
That's an 8 or a 4?
That's an H.
It's an H, I thought it was a 4.
It's an H. About the x-axis. And I want you to find the surface area of that solid of revolution as it whips around the x-axis. And then I want you to do the same thing about the y-axis. I want you to take the same thing here, just what I've got right here, around the y-axis. And find the surface area.
Getting sick again?
What's that?
Getting sick again?
No, it's just residual. It's just I'm talking way too much here. All right, so you guys do it.
Wait, this is for the first two?
You're going to do two problems. First problem, take the line y equals r, whip it around the x-axis from 0 to h, and tell me what the surface area of that solid revolution is. Well, you can do it. No, the integrals are real simple. So you can do the integrals. And then take the same area, here, the same thing, around the y-axis this time. And then find the surface area generated.
So,
You guys can do it.
how are we using a hypotenuse though for this angle?
What's that?
Are we using a hypotenuse?
Thought it was mine.
You're going to use the formula that I gave you.
Yeah, which had a hypotenuse, right?
The 2 pi y square root of 1 plus the derivative squared. Do the same thing. What's that?
Here, let me grab that.
Go ahead.
Yeah. I'm just not on this today.
So what's the difference between the normal surface area and the surface area over the x-axis?
Difference between what?
The two equations.
One is the surface area generated by taking that function about the x-axis. The second is taking it about the y-axis.
Oh. What about the one you gave us with the r?
R is going to be equal to x if you're going around the y-axis. R is equal to y if you're going around the x-axis.
I have more practice to do on.
You can stop recording it. That way there's 2 segments.